Okay, so on our last lecture, what we had done was, we are still looking at identical particles. We drive this Fermi-Dirac and Bose-Einstein distribution using the canonical ensemble. If you remember, first when we were looking at identical particle problem, we used the grand canonical ensemble, which was kind of easy to apply. And now we drive the same thing using the microcanonical ensemble. And then what we had done was we obtained, for example, such general relations between the pressure, volume, and the energy of a single particle in terms of its momentum. And then we also looked from a different perspective. We just said, okay, let's have this gas of molecules. They are moving around. They don't even have to be in thermal equilibrium. They're just moving around. They have some distribution. It can be thermal, it can be some other distribution we have. And then we had actually drive the same thing by just looking at how many particles are colliding with the given surface area per unit time. And that, which is nothing but the definition of pressure. And pressure again turned out to be just given by this expression here. This average of the P is the momentum, U is the velocity, that is the derivative of the energy with respect to momentum. Whatever the distribution you have, you just average over that distribution. Another application we did, which will be important when we discuss the black body, is so-called the effusion equation. So let's just imagine a box where you have some distribution of particles, not necessarily a thermal distribution, but some distribution of velocity of the particles. And if there's a hole on the wall, how many particles leave per second per area? So that is what's called the effusion coefficient. And we had seen that the rate of effusion, escape of these particles is given by the density. Well, that's kind of expected, is that if the density is high, the higher the density, there will be more particles escaping per unit time. And the average velocity times 1/4. Well, typically, if you would, let's say, just imagine particles moving left, right, up, and down in all three directions, if you would just say, okay, 1/6 moves in one direction, 1/6 moves in the other direction, in the opposite direction, etc., you would get 1/6, which is not far from 1/4, but the exact number is 1/4. Especially, again, if we apply this to black body radiation, just knowing the number of the effusion coefficient, U is constant C, the distribution is just a Dirac delta. So U is C, so the effusion of, if you want the effusion of energy, would be the energy density times C/4. That will be the amount of energy escaping this hole per unit area, per unit time. And when, again, that will be more relevant when we discuss the black body. What we call a black body is actually, that hole is the black body, not the box. But then, since all black bodies are identical, this would also give us the effusion coefficient of black body radiation. And, well, any questions from these topics? Because after this, we started a new topic. So if you have any questions about these, anything you want me to repeat. Then we looked at the problem of, up to here we were discussing gases and treating the gas molecule, gas particles as point objects without any internal structure. Then the question is, what happens if they have internal structure? So basically you can just, assuming still the molecules, whatever they are not interacting with each other, but now we want to ignore the internal structure. So what will happen is, again, we can separate the translational motion and the internal contribution from the internal microstage. So basically, you see, this is the partition function of a single particle, point-like particle within a volume V. And then this J of T is what represents the contribution from the internal degrees of freedom. And in fact, once we know J of T, we know the endpoint particle function, then we know the free energy, we can calculate the entropy, the energy, the specific heat, etc. We can calculate all of them. And basically, we will continue along those lines today. But before continuing, okay, there are a couple of numbers to keep in mind. If you remember the hydrogen atom, for example, the energy of the hydrogen atom is around minus 10 electron volts, the ground state. To excite the hydrogen atom, you have to provide an energy larger than the electron volts. And typically, to excite electrons in an atom, you have to go to higher energy levels, you have to give them an energy of the order of electron volt. And remember, room temperature, which is 300 Kelvin, is 1/40 electron volts. So 1 electron volt basically typically corresponds to 10 to the power 4 electron volts. 10 to the power 4 Kelvin, 1000 Kelvin, 3 times the room temperature. 1 electron volt, 10 to 3 Kelvin. And basically at room temperature is very cold for electronic excitations. So at typical temperatures, we can basically ignore them. Of course, again, if you look at the electrons in atoms or molecules, you get spin orbit coupling, which is called the fine structure. Well, the splittings in the fine structure correspond to typical temperatures around 10 to the power 2, 10 to the power 3. So room temperature is typically of that order of magnitude. We can go to very high temperatures or low temperatures, but the fine structure will be relevant. At room temperature, we can excite the fine structure levels. There's also the hyperfine splitting, which is caused by the interaction of the nuclear spin with the electron spin. And these hyperfines, the energy splittings corresponds to of the order of 1 Kelvin. So typical room temperature, or even as long as you don't go to microkelvin temperatures, these hyperfine splittings, we can basically ignore them. We can just assume that they are all degenerate. For the ionic excitations, and for the electronic excitations to higher energy levels, well, we can just assume we are too cold for them. There won't be any contribution. When we look at molecules, typically to separate the molecules, to dissociate the atoms in a molecule, we again need to provide energies of the order of electron volts. And room temperature is too cold for that. There won't be any dissociated molecules at room temperature. And now when we look at vibration molecules, we will also look at cases where there's the vibrations. Typically, vibrations have an energy of the order of 10 to the power 3 Kelvin. Well, it's higher than room temperature, but not that high. I mean, 1000 Kelvin is not that difficult to reach. And there's also rotational degrees of freedom. These molecules will rotate around some axis, might rotate around that axis, and the rotational energy levels will also be discrete. The energy splitting will be, depending on the molecule, tens of Kelvin. So at room temperature, most of them will be excited. But if you go to very low systems, then you won't be able to excite the rotational degrees of freedom. So these are some of the energies that you need to keep in mind. So any questions in these numbers? Yeah, of course, in almost all cases, we will just look at the high temperature and the low temperature limit. So for simplicity, let's look. Now, J of t, remember, this was equal to the internal degrees of freedom e to power minus epsilon kt. And remember what we mean by internal degrees of freedom. There will be some electronic energy levels of my system. There might be some vibrational degrees of my system, for my system, so they will also separate. And there will be some rotational degrees of freedom. And also the rotations will basically be the rotations of the nuclei among themselves in a multi-atom system. And then nuclear degrees of freedom. This will be basically, I mean, the nuclear excitations are of the order of MeV. I mean, electron volt is already a too high temperature for a room temperature. nuclear energy levels, we won't be able to excite them, but still the nucleus has spin. So this will be what I call the nuclear degrees of freedom, will be mainly the spin degrees of freedom. And as we will see later on, these two will be really coupled to each other. I mean, you cannot really separate one from the other one. The problem will be, I mean, the nuclei can be bosons or fermions, and rotations are related somehow to symmetry or anti-symmetry of the wave functions under the exchange. Rotations are related with the exchanges. So you have to, we will have to take that into account. So we will treat the rotation and the nuclear spin degrees of freedom together later on. It will be more obvious later on. That is probably the hardest part in all this derivation. So when we look at monatomic gases, yeah, there's no vibration. Nothing vibrates. There's no rotation. And there's no nuclear spin. The only degrees of freedom here will be the electronic degrees of, well, okay. There is the nuclear spin. Electronic degrees of freedom, and there is also the nuclear degrees of freedom. And typically, if L is equal to 0, let's say, if L is equal to 0, L is L of the electrons, so there's no spin orbit coupling. All the states are almost degenerate. So J of t for this case will be, well, there can be a spin. This is the degeneracy from the spin degrees of freedom. There is also the nuclear spin. Yeah, basically this is it. This is our partition function. It is constant, it doesn't depend on time. Well, you can also have e to power minus epsilon 0 over kt, but this just gives a constant shift in the energy independent of temperature. Remember, if this is J of t, the free energy will be minus kt times logarithm of J of t, which will be minus kt logarithm of 2se plus 1, 2sn plus 1 plus epsilon 0. This is the free energy of the system. The entropy will be minus the derivative of free energy with respect to temperature. This is just k times logarithm of 2se plus 1, 2sn plus 1, so it's just a constant. Well, that's not a big surprise. Remember, the entropy of a system was the logarithm of the number of states that the system can be in. If my state can be in this, due to the degeneracy of the electronic and the nuclear spin states, I have this many internal states correspond to corresponding to each of the translational degrees of freedom. So the number of microstates my system can be in is just gets multiplied by this factor. That's the number of states, and hence that causes an increase in, well, let me divide by n. This is per particle. So now the entropy just increases by this factor. Now, when L is non-zero, we have spin orbit coupling. This is the fine structure. Well, fine structure can be close to the room temperature, so we should take that into account somehow. The JT will be given by sum over all possible values of J of my system of 2J plus 1 e to power minus epsilon J divided by KT. Well, again, you can go to very low temperatures. If you are at very low temperatures, then J of t will be approximately given by 2J0 plus 1 e to power minus epsilon J0 divided by KT. J0 is the J value that has the minimum energy. In this case, basically, we are back to this case where there is an additive constant to entropy and additive constant to chemical potential. Nothing so much interesting. If you are at the very high temperature limit, at very high temperatures, you can just assume that your system is degenerate. You can ignore the energy splittings. Then J of t would be basically epsilon tilde is a typical energy of your system, because I'm at a very high temperature. The splittings I just ignore, so all of them I can treat as degenerate. The splittings will be much smaller than KT. And this epsilon tilde is just any one of those values. Well, the sum over J would just give me 2SE plus 1, 2L plus 1 e to power minus epsilon tilde divided by KT. Plus, of course, there's the nuclear spin degeneracy, which I'm not writing down here. But again, we are back to the previous case where the energies are shifted, chemical potential is shifted, entropy receives a constant contribution, the specific heat doesn't get any contribution. Since there is a constant addition to the internal energy, well, the specific heat is just a derivative of energy, so that constant is 0. Well, you can have some intermediate energy levels, intermediate temperature, where it might be that J of t will be, let's say, some levels plus, let's say, just take one other energy level. I mean, we will also see such cases when we look at the molecules. So it might happen that, okay, the first term is small, but not very small. The second term, third term, we can just ignore. So this can be our J of t, the partition function corresponding to the internal degrees of freedom of a single atom. Then we can ask what will be the energy levels, the contribution to the energy, entropy, etc. Well, let's calculate the free energy is just log minus KT logarithm of JT, which is minus KT logarithm of the energy, again from a single particle, will be minus the derivative with respect to beta of logarithm of J of t. So, which is minus the derivative with respect to beta of G0 plus the logarithm of G0 plus G1 e to power minus epsilon divided by K of t, which will be, 1 over K of t is just beta. So if we take this derivative, what we will get is epsilon G1 e to the power minus beta epsilon divided by G0 plus G1 e to the power minus beta epsilon. This will be the energy of my system. The specific heat, the contribution to the specific heat will be the derivative of energy with respect to temperature. Well, let me write this in a slightly different form. Derivative with respect to temperature of epsilon divided by G0 over G1 e to the power beta epsilon plus 1. I just multiplied the numerator and denominator by e to the power beta epsilon over G1, so that at least the temperature appears only in a single place. Well, this derivative is now easier to evaluate. It will be minus epsilon divided by G0 over G1 e to the power beta epsilon plus 1 squared. Now the derivative of the numerator will give me, with respect to t, well, first let me take the derivative with respect to beta. That would give me epsilon G0 over G1 e to the power beta epsilon. Now take the derivative of beta with respect to t, which will be minus 1 over kt squared. So these minuses cancel, so let me write it as epsilon over t kt squared. This is the, again, I remind you, this is the contribution to the specific heat, times k, times 1 over 1 plus g0 over g1 e to the power epsilon over kt times 1 plus g1 over g0 e to the power minus epsilon over kt. Well, the reason why I write it in that form is if you would like to sketch the specific heat as a function of temperature. Now, let's see, if you go to very low temperatures, at very low temperatures, this will be large. It will become very large. This will become negligible. Well, this exponent is in the denominator, so you have 1 over a very large number, so you basically go to 0. So here you have a expression that goes to 0, and it goes to 0 as k times epsilon over kt times g1 over g0 e to the power minus epsilon over kt. It is this term that dominates the behavior at t equal to 0. Now, if you go to very large temperatures, well, at very large temperatures, this epsilon over kt is practically 0. So you have e to the power epsilon over kt is 1, e to the power minus epsilon over kt is also 1. So this is just a constant, but then we have a 1 over t squared there. So at very large temperatures, again, it goes to 0. And somewhere in between, it should have some maximum value. And typically, this is at some value where kt is of the order of epsilon. So at least if you are able to measure this contribution to the specific heat from a single molecule, you would expect such a peak somewhere at intermediate energies. And from the position of that peak, you can even determine the energy level, the internal energy level energy. Well, basically, that's all we can say about the monatomic gases. Now we can go to, let's say, diatomic gases. Well, in the case of diatomic gases, well, in the monatomic gases case, well, there's no vibration, there's no rotation. Nuclear spin just gives a overall multiplicative factor, which I didn't write over here. So this J nuclear. It's just a constant. Now let's come to the diatomic system. Now we will need to separate two cases. Heteronuclear molecules and homonuclear. The reason is, if they are of the same molecule, we have to also, they are indistinguishable, so we have to pay attention to whether they are bosonic or fermionic. So we have to treat them separately. So let's see. Let's start with the heteronuclear case. And let's look at the vibrational degrees of freedom. Well, basically we have these two atoms bound, they are bound by a chemical bond, they can just vibrate along the axis connecting the two atoms. And we know the energy levels. H bar omega n plus 1 over 2. Let me just ignore the ground state energy. They will just give me a shift. So the partition function, due to this rotational degrees of the vibrational degrees of freedom, will be just sum over n from 0 to infinity e to power minus h bar omega raised to the power n, which is nothing but 1 over 1 minus e to power minus h bar omega over kt. Let me write this as 1 over 1 minus e to power minus theta v over t. Theta v is defined as h bar omega over k. And you see, for the vibrational degrees of freedom, that theta v is around 1000 Kelvin. So close to room temperature, you start exciting them. Room temperature is not that small. It's low temperature, but not that low. So the free energy, let's just look at the energy directed. The energy corresponding to vibrational degrees of freedom will be minus derivative with respect to beta logarithm of j of t, or derivative with respect to beta of logarithm of 1 minus e to power minus beta h bar omega. If I take the derivative with respect to beta, I will get h bar omega e to power minus beta h bar omega divided by 1 minus e to power minus beta h bar omega, which is just h bar omega divided by e to power beta h bar omega minus 1. As this, if you note, this just looks like the Bose-Einstein condensate with zero chemical potential. And it's not a coincidence because, okay, on one hand I have these vibrations, this oscillator, this molecule vibrating, but this oscillator is just a collection of energy packages of h bar omega. So each one of these energy packages has an energy h bar omega, and they are bosons. So if you just look at the statistics of the energy packages themselves, rather than the atoms vibrating, well, they are bosons. The energy packages are bosons. So hence they satisfy Bose-Einstein statistics. So that's why we recover this Bose-Einstein statistics. And since their number is not conserved, they're just like photons. Their numbers will not be conserved, and hence their chemical potential is zero. Okay, now let's look at the specific heat for the system. The specific heat for the system will be the derivative of energy with respect to temperature. Well, let me first take the derivative with respect to beta. This will be minus h bar omega divided by e to power beta h bar omega minus 1 squared times derivative of the denominator with respect to beta, which will be h bar omega e to power beta h bar omega times the derivative of beta with respect to t, which is minus 1 over kt squared. Again, these minus signs cancel. We end up having k h bar omega divided by kt squared times 1 over e to power beta h bar omega minus 1 times 1 minus e to power minus beta h bar omega. Well, just like similar to the previous case that we had considered. Let's look at the high temperature limit. You see, the high temperature limit will basically correspond to h bar omega times beta, which is h bar omega over kT. This is much, much less than 1. If this is much, much less than 1, I can just expand all the exponents in beta h bar omega. So CV would be k h bar omega over kT squared times 1 over 1 plus beta h bar omega plus beta h bar omega squared over 2 minus 1. This is the first term. This is the expansion of this one. Then I would have 1 minus 1 plus beta h bar omega minus beta h bar omega squared over 2. I would like to calculate the first correction. That's why I'm just expanding up to beta h bar omega squared. I'm just ignoring higher order terms. This is k h bar omega over kT squared. You see, these ones cancel. Both terms have 1 over beta h bar omega factors squared. What is left is 1 plus beta h bar omega over 2 and 1 minus beta h bar omega over 2. Well, I will probably need one more term. Here I have beta h bar omega squared over cubed over 3 factorial, again plus beta h bar omega cubed over 3 factorial. So what is left is 1 plus beta h bar omega over 2 plus beta h bar omega squared over 3 factorial, 1 minus beta h bar omega over 2 plus beta h bar omega squared over 3 factorial. Now the reason why I'm adding one more term is if you just keep these terms, if you multiply them, then you get 1 minus beta h bar omega over 2 squared. But those squared terms I ignored. So that won't be consistent. I will also get beta h bar omega squared terms from these terms. So that's why I had to keep them. So these cancel the overall coefficient. So I have k times, well, 1 over, let me just keep the first non-zero contribution. That's what I'm aiming at. First non-trivial contribution, first contribution. If I just ignore all beta h bar omegas, then CV is just k. Now that is what we had already derived classically. And oscillator contributes to specific heat. The specific heat of a gas of oscillators is just nk. Per oscillator, we just have k. This is what we had already derived, this first term. Now, let's look at the second term, the first correction. If I multiply these out, you see, I have 1. Beta h bar linear terms will cancel. I will have beta h bar omega squared terms. They will come from the product of these two. Which will be minus beta h bar omega over 2 squared. Then I have from these terms, if I multiply them with this 1 over here, I also get those corrections. They will be plus twice beta h bar omega squared over 3 factorial plus higher order terms. This is what I should get. Well, let me simplify them. This is k 1 over 1 minus beta h bar omega squared, 1 over 4, this is the first term, and from the other term I have minus 1 over 3, right? Three factorial is 6, I have this 2, this is, yeah. which is k times 1 over 1 minus beta h bar omega squared. Well, that difference is 1 over 12. This is k times 1 minus beta h bar omega squared over 12 plus terms of the order of theta vibrational divided by t to the power 4. There will be higher order corrections. What does this tell me? Okay, this is the, we know that this is the high temperature limit. This is the classical limit K. This tells me that at high temperature, it approaches the classical limit from below. If I didn't make a mistake in my signs, it approaches it from below. At low temp, this is the high temperature limit. At low temperatures, you see, this is my specific heat. At low temperature, that is when beta is very large. When beta is very large, this term is 0. This term is very large, so CV is k times h bar omega over kt squared times e to the power minus beta h bar omega. So it goes to 0 exponentially. So this is what I would get for the specific heat as a function of temperature. I calculate two extreme limits and then just try to connect them smoothly. So any questions on the vibration? Well, I mean, it's basically what I'm doing is just first identifying the microstates, what are the quantum numbers specifying my microstates, and then summing over all the microstates this exponential function. And then the rest is basically algebra. And what we can, for example, this is an experimentally observable prediction. Within this framework, if there is only one state contributing to my partition function, besides the ground state, there's just another one contributing to my partition function. This is what I would expect from the partition, from the specific heat. By measuring the specific heat, I can determine the energy levels. Here, in the case of rotational degree, vibrational degrees of freedom, I know that at low temperatures it will be 0. At high temperatures it will just reach the classical limit. What is the transition point? Well, this is typically the transition temperature. This is of the order of 10 to the power 3 Kelvin, let's say, depending on your molecule, of course. So if you have a gas at, I don't know, 10,000 Kelvin, well, still, there won't be many dissociated atoms. Most of them will still be intact, but the vibrational degrees of freedom will be excited, and hence you will measure the contribution to the specific heat. If you look at a gas at 100 Kelvin, well, vibrational modes will not be excited, so you won't get the contribution. Now let's look at the rotational degrees of freedom for the system. Again, we also have the nuclear properties, but the nuclear properties, they are just degenerate nuclear energy levels. So they just contribute 2Sn plus 1, just a multiplicative degeneracy factor. Rotations. Now the Hamiltonian for rotations will be just L squared over 2I. So the energy levels will be just H bar squared L plus 1 over 2I. The partition function, sum over all L and M, I have two quantum numbers for angular momentum L and M, of e to power minus beta epsilon L. Well, energy levels do not depend on M, so I can just sum over all M. This will just sum over L from 0 to infinity, 2L plus 1 for each L. I have a corresponding 2L plus 1 M values, e to power minus beta h bar squared L plus 1 over 2I. So here we define some characteristic temperature for rotations as h bar squared over 2I times 1 over k. So this jt would be L from 0 to infinity, 2L plus 1, e to power minus theta r over t times L plus 1. So you see, high temperature basically means corresponding to this rotational temperature, high relative to that one, and low temperature basically means corresponding to that theta r. Now high temperature limit, or let's say low temperature limit, which means theta r over t is much larger than 1. If theta r over t is much larger than 1, then we have j of t, basically the L is equal to 0 term contributes, higher L values don't contribute. J of t will be just L is equal to 0 term will be just 1. If you want to calculate the first correction, then you can take the next term plus 3 e to power minus 3 theta r over t, plus of course you have all the other corrections. Well, we are back to the first case we discussed at the beginning of the lecture. For such a partition function, at low temperature, the specific heat goes to 0. At high temperature, again, the specific heat goes to 0. You have some kind of a maximum at some intermediate values. Of course, high T, we cannot really go to high T because we are already at the low temperature limit. But at least we know that at low T it goes to 0. Now let's look at high T. You see, if T is very large, for reasonable values of L, that exponent is very small. The number in the exponent is very small. It's very close to 1. So the exponent itself is almost 1 for a large number of L values. Or not very small, let's say. Only if when L becomes much larger than T over theta r, that exponent factor becomes very small. But that is a large value of L, and not the overall factor 2L plus 1. For L less than this value, or let's say the square root of this value, since I have L squared there, e to the power minus theta r over t L plus 1 is typically 1. But t over, since we are at the high T limit, that t over theta r is very large, so there are a large number of L values contributing to my integral, and in fact, the dominant one will be the large L values because of that 2L plus 1. But if the L values, large L values are dominating, then I can just approximate j of t by this integral. Remember, at large values of L, that function changes more or less mostly Since the function changes more or less smoothly at large L values, I can replace the sum by an integral. Of course, this won't work for small values of L, but the main contribution is already at large from large values of L, because we are at the high temperature limit. Now, I can just improve this slightly, let's say by using this expression. You see, a sum over integers, we can replace it by an integral. That is the first correction, but then we have higher order corrections. So let me also look at those corrections. Plus 1 over 2 derivative with respect to L, 2L plus 1 e to power minus theta r over t, L plus 1, evaluated at L is equal to 0. Then I have plus 1 over 720. This is the third cube. So this is the approximate expression. Let's start with the first term. Let's start with the integral 0 to infinity dl 2l plus 1 e to power minus theta r over t, l squared plus l. Note that I can write this as from 0 to infinity dl e to power minus theta r over t, l squared plus l. Take the derivative with respect to l of the exponent. If I take the derivative with respect to L, I will get a minus theta r over t. So let me multiply by minus t over theta r. And then I will get 2L plus 1. That is why, so this integral is kind of easy to evaluate. Now it's the integral of a total derivative. So I have the integral is minus t over theta r e to power minus theta r over t, L plus 1. L goes from 0 to infinity. And at infinity, that exponent just basically goes to 0. At L is equal to 0, the result is just t over theta r. Let me write the 0. The first.
What
Yes.
happened to do d square over dl square term in the expansion?
Which one? These, the second and the third terms. Well, that's why I wrote this 0 over here. I'm just looking at the first integral, this term. I'm just calculating this term. I will add the higher order corrections later on. And in fact, the reason why I'm adding the higher order corrections would be, let's say this is J0 of the energy corresponding to this expression would be minus the derivative with respect to beta of logarithm of j of t, which is 1 over beta theta r. Beta is 1 over kt, so let me just put the k also over here. This is just derivative with respect to beta of logarithm of beta. So this is 1 over beta. This is the energy. Specific heat will be the derivative of the energy with respect to temperature. This is just K. Well, we have two rotational degrees of freedom. Since this is just a line, you see there is this rotation around this axis. There is, okay, so it's a line. There is this rotation. There is also this rotation. There are these two different rotations. I don't have this rotation. I cannot excite that rotation because if you try to rotate this molecule around its axis, its moment of inertia for rotations around its own axis is 0. So the energy level will be, the energy will be h bar squared L plus 1 over 0. So that would, quantum mechanically, that would require a very high energy. So I cannot excite these rotations around its symmetry axis, around its axis of this diatomic molecule. I only have 2 different degrees of rotations. And hence, each degree of rotation contributes k over 2 to the specific heat. This is our classical result. What is the first correction? So how do we approach this classical result? Do we approach from above or from below? For example, that is one thing we should ask. That will be from these correction factors, but let's leave it to the next hour. Again, it's just kind of boring computation. It's straightforward. Identify the energy levels. Once you identify the energy levels, sum the Boltzmann exponent over all the microstates, and then try to interpret what you have. We are calculating the specific heat because that is something that we can easily measure. So we can compare it with experiments. So any questions before you go for a break? So see you in 10 minutes. Have a walk, some coffee.